Okay, so this is a graph of f, and we're going to define g to be the integral from 0 to x of f of t dt. So before I even ask you the question, how is g of x related to f? It's an integral. Yeah, yes. G of x is the integral from 0 to x of f of t dt, right? What is FTC part 2? That defines this to be an antiderivative of f. Okay, so now we know g of x is an antiderivative of f. Okay, so let's think about g of x. Which of these? Increasing concave up, decreasing concave up, increasing concave down, decreasing concave down. So derivative function, g is an antiderivative, so we can look at the sign and the increasing decreasingness of it. So we're only looking 0 to 2. Right? So from negative 1 to 0, f is positive, which means its antiderivative is increasing. So here I'll put g increasing because f is positive. And f is increasing, which means that g is concave up. And then from 0 to 2, g is positive. I'm sorry, f is positive, which means that g is still increasing. But now f is decreasing, which means that g is concave down. Right? So they only asked us about 0 to 2. So we're just talking about increasing concave down. Let's see. Good. All right, so we're going to learn many, many techniques for finding antiderivatives this semester. The most widely used of these techniques is the one we learned today. And we're going to continue talking about it next class. In the same way that the chain rule allowed us to differentiate many new functions last semester, this method, called the substitution method, is going to allow us to anti-differentiate many new functions. So spend time in the coming weeks reviewing the material from this section. If you don't get good at substitution, much of this semester will be a struggle. No pressure. All right, so many integrals that we will encounter will not initially be one of the few forms that we've studied so far. So right now, all we can really do is look at our table of functions that we know the derivative of, and if one of those derivative, if we happen to know the derivative, we can go backwards, right? But we have a powerful technique known as the U-substitution method that can convert a bunch of unrecognizable integrals into easy integrals. So it's sort of the like age-old mathematician's approach is try to turn it into something easy. Right? All right, so we're going to try to find an integral of x squared plus 1 to the 50th times 2x dx using a substitution method. Okay, so the key to U substitution is to choose something in the integrand to make a U. Okay. I'm going to make a substitution, so I'm going to choose some expression from the integrand and say, let that be U. And the key to making the choice of what U should be is you should choose the most complicated thing you can, whose derivative also shows up in the integrand. So go ahead, say it again. X squared, can you make it even more complicated? X squared plus 1, because the derivative of x squared plus 1 is 2x, and 2x also shows up in the integrand. Okay, so we're going to say let u be x squared plus 1. All right, so that means that du dx would be what? 2x. Now, treat du dx as a fraction, even though we know it's not really a fraction, and solve it for dx. What would dx equal? Close. Du over 2x, yeah. Multiply both sides by dx, divide both sides by 2x. Okay, so now I'm going to take my integral and rewrite it using u's instead of x's. So instead of x squared plus 1 to the 50th, 2x dx, this is going to become the integral of, instead of x squared plus 1, I'm going to use a u to the 50th, times 2x. I can't really do anything with that yet. But then I have to replace my dx, take this dx and replace it with a du over 2x. And oh, how magical it is. The 2x's cancel. And then I just have to take an integral of u to the 50th du, which is super easy now. Just do the reverse power rule. So what made this work, the reason the u substitution worked, was because I chose the u so specially so that its derivative also showed up in the integrand, because the derivative has to cancel. Right? All right, so now to finish, the integral of u to the 50th would just be u to the 51st over 51 plus c, and then you can substitute your u back in, x squared plus 1 to the 51st over 51 plus c. It doesn't seem that hard, right? It's okay. Once you do a few, it gets easier and easier. Okay, so we'll do one more. Integral of cosine 5x. Is there a function in there whose derivative also shows up in the integrand? Yeah, there isn't in this case. But what's sort of the innermost function? 5x. And what's the derivative of 5x? 5. Okay, so when the derivative is a constant, that's sort of easy to compensate for, because you can always just, when you're taking an antiderivative, multiply by another appropriate constant to get rid of it. So if you can choose, if there isn't something whose derivative shows up, choose the most complicated thing. So your derivative might be off by a constant. That's okay. So in this case, we're going to choose let u be 5x, which means du dx is 5, which means that dx would be du over 5. So then we go ahead and make our substitution. So this is sort of all our preliminary work. Then we take the integral of cosine 5x dx, and I make my substitution. This is going to become the integral of cosine u, and instead of dx, I put a du over 5. And the reason the constant thing didn't matter is because when you have a constant in an integral, you can pull outside the integral. Right? So I could rewrite this as 1/5 times the integral of cosine u du. Okay, so we have that really nice property of integrals, that if you have an integral constant within the integral, you can just pull it out. And then, so this is going to become 1/5. What's the antiderivative of cosine? Sine of u plus c, and then replace the u with a 5x. 1/5 sine 5x plus c. And this one, we most certainly probably could have come up with an antiderivative without doing U substitution. Right? I could have just said, okay, well, antiderivative of cosine is sine, but then think about taking the derivative. The sine of 5x, its derivative would be cosine 5x times 5. So we throw this 1/5 in front to make the 5 cancel. But this is just a formal writing out all the work to show you how U substitution works. Okay, so let's look at the beginning of the packet. There's a guide to U substitution there. Let's take a quick look at the walkthrough step by step, how it works. All right, we're on page 43. U substitutions is on the second page. So you let U equal some stuff. It may take several guesses for you, right? So sometimes it's really obvious what the U will be, because the ideal is that you would pick U to be something whose derivative also shows up in the integrand. But sometimes it will take more than one guess, and that is totally normal. And don't get frustrated if you have to try 2 or 3 times to find a U that will work. Step 2, find du dx and solve for dx. Step 3, rewrite the integral by putting in U instead of the stuff and replacing dx with what you got in step 2. Step 4, cancel, 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 simplify, simplify, simplify. Everything that's left should be U's. There should be no X's left. If there are any X's that didn't cancel, you should go back and try a different U. All your X's should be gone. Integrate with respect to U, replace the U with the stuff, and then you can check by taking the derivative of your answer, and it should bring you back to where you started. Hints for choosing U. These are just some different kinds of things you might see. Let U be the stuff in each of these. So this page you can use on your test. So there are no hard and fast rules as to when a U substitution will work. Sometimes there's trial and error involved in the choice of U. It's normal and expected. It can be frustrating, but doesn't mean that you should give up if your first choice of U doesn't work. Sometimes you really just can't see ahead of time what choice of U will work. Basically, you're looking to split the integrand into the product of 2 functions, one of which is the derivative of part of the other, possibly differing by a constant multiple. So you're looking for a function whose derivative also shows up, but it might be off by a constant multiple, and that's okay. So for example, what would you choose for U in each of these examples? Well, this first one we already did, right? We let U be x squared plus 1. All right, in B, what would your first choice for U be? The stuff under the radical, yeah. Because you want to choose the most complicated thing you can, because you want to simplify it by replacing as much as you can with a U. And you want to choose something to be U whose derivative also shows up somewhere in the integrand. So when I look at this stuff under the radical, 3 minus 5t to the 5th, well, the derivative of 3 is gone, and the derivative of 5t to the 5th is 25t to the 4th. And I have a t to the 4th in here. So that makes it a good choice for U. The constant we can deal with easily because you can pull constants right out of integrals. Okay, how about in C? What would you choose as U? The whole denominator. Yeah. The whole denominator, because its derivative would be 2x plus 10, which is just double the numerator, right? It's just the numerator differing by a constant. All right, for D, we have e to the 4x times the sine of e to the 4x. What would you choose as U? 4x. That would still leave you with e to the u times the sine of e to the u, which is not a function coming from a derivative. We don't know a function whose derivative is e to the u times sine of e to the u. Can you e to the 4x? Yeah. So that would become the integral of u sine u, which is still a tough one. How would you integrate that? We'll learn that another day. Okay, so maybe we should do a couple of these. We did this one. Let's look at B. Let's finish this problem. We've chosen u. We're going to finish the substitution. Okay, so we've got u. Let's calculate du dx. So what would du dx be? Negative 25 t to the 4th. Yep. Sorry, I should have done du dt. My independent variable is t in this problem. Then I should solve for dt. So I would treat dt like a fraction, right? You can think of it as cross-multiplying if you want. And I want to solve for dt, so I end up with du over negative 25 t to the 4th. So then I go back to my integral, t to the 4th times the square root of 3 minus 5t to the 5th. Yep, thank you. All right, so this is going to become the integral of t to the 4th. I don't have a substitution for that yet. Times the cube root of u. And then instead of dt, I'm going to rewrite this as du over negative 25 t to the 4th. Okay. So that's like steps 1, 2, and 3, right? Choose a u, find du dt and solve for dt, and then make all your substitutions. Step 4 is cancel and simplify. So when I'm done canceling, there should only be one variable left, and it should be u. So my t to the 4th, I have one up here and one in the denominator. Those cancel. And then I have a negative 25 in the denominator, this constant. I can bring that right outside the integral. So this is going to be negative 1 over 25 times the integral of the cube root of u, that's u to the 1/3 du. Okay, so now the antiderivative of u to the 1/3 is a much simpler problem than what we started with. Add 1 to the exponent, so 3/3 plus 1/3 is 4/3. And then divide by 4/3, which is the same as multiplying by 3/4 plus c. And then I'm going to simplify by multiplying the two fractions. And then my last step is to replace the u with 3 minus 5t to the 5th. So this is negative 3/100 times, I forgot what it was already, 3 minus 5t to the 5th to the 4/3 plus c. And we should check. I mean, there's no reason to ever not know that you got an antiderivative wrong, right? So we took an antiderivative, which means that if I did the derivative of this, I should get the original function back. So let's do that. just to get in the habit here. Okay, ddt of all that stuff. So when I take the derivative, I'm going to start with the outermost thing, right? I'm going to do the power rule, bring the 4/3 down. -3 1/100ths times 4/3, the 3's cancel, and I'm going to get -4 over 100 times 3 minus 5t to the 5th to the 1/3. Then I have to multiply by the derivative of the inside stuff, which is what? -25t to the 4th. And -4 over 100, that reduces to -1 over 25. So that cancels with that. And you're just left with t to the 4th times the cube root of 3 minus 5t to the 5th, which was our original integrand. All right, why don't you guys try C? You already get the u. See if you can just apply the procedure, get the antiderivative. Okay, so we've got a u chosen already because we chose a u whose derivative or something close to its derivative also shows up in the integrand. So that way when I take du dx, I get 2x plus 10, which means that dx is going to be du over 2x plus 10. So those are the first 3 steps, and it's like really procedural. Pick a u, find du dx, solve for dx. Then you make all your substitutions. So we have the integral of x plus 5 over x squared plus 10x minus 41. That was our u. Right? And then replace dx with what we solved for. That would be du over 2x plus 10. And this is the part where you simplify and cancel as much as you can, and you just like have your fingers crossed, hoping that all the x's go away. Right? So this is going to be x plus 5 over u times du. I can factor out a 2 from this 2x plus 10, which means that I will get all my x's to cancel. So this becomes the integral. I'll bring the 1/2 out in front. 1/2 the integral of 1 over u du. And what function has as its derivative 1 over u? Yeah, ln. So this is 1/2 ln. It's actually absolute value of u, because you can't plug negatives into the ln function. But then u was that polynomial, that quadratic polynomial. So this is just make that last substitution. X squared plus 10x minus 41. Okay. Good. We're going to skip D because it's actually not possible yet. This is a correct u substitution because it would simplify quite a lot to be u times the sine of u. But then dx, oh, actually, no, we could do this one. Let's do it. Yeah. Sorry, I'm wrong. Because the derivative will cancel. Okay, so we've got u. Choose it as the innermost. You kind of want to choose a u that's an inside function. And you want to choose it so that its derivative also shows up, right? So if I make e to the 4x, right, if I make that my u, its derivative is also e to the 4x times 4, but the constant multiple we can deal with. All right, so u is e to the 4x. That means du dx is 4 e to the 4x, which means that dx would be du over 4 e to the 4x. All right, so then my integral, I could replace e to the 4x with a u. So some people may have done that, and some people may have recognized the need to leave it out so that you can cancel this. Either way is fine because you can see the cancellation before or after. Right? Yeah, right. So which one did you do? Did you make it a u? Okay, so let's write u. And this becomes sine of u. And then dx is going to be du over 4 e to the 4x. But e to the 4x, that's u, right? So this would be over 4u. So you can either have left this u as an e to the 4x and this as an e to the 4x and cancel those, or make them both u's and cancel those. As long as at some point you recognize that what's up here and what's down here are the same thing, then they can cancel. So then I just have to bring a 1/4 outside the integral. And this just becomes the antiderivative of sine u. Okay, what function has as its derivative the sine function? Negative cosine. This will be negative 1/4 cosine u plus c. And then u is e to the 4x. All right, so are you starting to develop a little bit of comfort with the procedure? Okay, that's good because now you have a bunch to do for practice. No substitute for substitution. One of these, oh, sorry, there's still like 1, 2 or more sentences I want to say before you start that. I'm going to skip the challenges for now. If you just look at number 8 here. The technique does not always yield a tractable integral, right? So that means an integral that's possible to do. Okay. So keep in mind, if you end up with both u's and x's in an integral after you have substituted and canceled and simplified, the u substitution you just tried won't work. You have to go back and pick a different u. Okay. And sometimes there is no u substitution that will work. For today, I'm not giving you anything that won't work. But so for example, here's one, 2x times the sine of x to the 4th. So if I were to try to use u substitution here, what might you choose as u? X to the 4th, yeah, sort of the innermost function. So then du dx would be 4x cubed, and that means that dx would be du over 4x cubed. So when I make my substitution, I get the integral of 2x times the sine of u times dx, which is du over 4x cubed, and 2 cancels with the 4, and x cancels with my x cubed, and that becomes an x squared. So now I have the integral of 1 over x squared, 1 over 2x squared, sine u du, and I'm stuck, right? I have x's and u's in this integral. I cannot finish this. After you've done all of your substituting, all the x's should go away. If they don't, you got to start over and pick a different u. And if you've tried 3 or 4 or 5 different u's and you can't make it work, maybe u substitution won't work on this, and you got to try a different technique. As of today, this is the only technique we have. So if it doesn't work, you just move on. So note, u substitution doesn't always work on the first attempt. If at first you don't succeed, you are not necessarily a failure, right? Try 2 or 3 or 4 more times. Keep at it until the integral is completed. At some point, it might be that a u substitution won't work and you got to try a different technique, but not today. Okay, so now I've got a bunch for you to practice. One of them cannot be easily done with the tools you currently have. So if you get stuck, move on or call me over and I'll tell you if that's the one that you can't easily do.